Now we will arrive at the BCS theory, and BCS theory is a fundamental theory in superconductivity. BCS theory. BCS theory is the abbreviation of the name of physicist Bardeen, Cooper, and Schrieffer. Bardeen is famous for whom get a Nobel Prize twice, and one is with Shockley. He developed theory for the semiconductor, and the second Nobel Prize is for this BCS theory. And anyway, then Bardeen is a theorist, and Bardeen can solve the semiconductor device problem. And after that, Bardeen considered for the theory of superconductivity, what causes the superconducting state. And he recruited the postdoc Leon Cooper. And Cooper is a theorist, particle high energy physics, high energy physicist. And Cooper invited as a postdoc in the Bardeen group. And in this time, the basic concept of BCS theory is Cooper pairs. And Cooper developed the concept for Cooper pairs because basically, as you know, and as I said, superconducting state is a macroscopic quantum phenomena, and also is kind of Bose condensation because the kinetic energy of electrons has the same identical energy, and the kinetic energy is almost the same with each other, and it is kind of macroscopic Bose-Einstein condensation, and therefore the Bose-Einstein condensation should have the bosonic particles, and but the electron is not a bosonic particle because electron have the 1/2 spin, and in order to have the bosonic particle formation of the electrons, and they should have considered for the spin up and spin down coupling, and it is Cooper pairs, and total spin is 0. And the p-part non-local theory also deal with the coherence lengths, and anyway the two electrons mediated any kinds of basically it is a phonon, but any kind of mediation for two electrons, and there is a non-local distance, and we call it is a coherence lengths. And during the meantime, and p-part non-local theory surmise that a quasi-particle, not the exact particle. But when we think about that the exact particle, and the local theory is enough to describe the superconductivity, but even the phenomenological theory and the local theory, it doesn't apply to the superconductivity. It means that the quasi-particle excitation should be considered. The second thing for the quasi-particle requirement is that they should have the bosonic particle. It means that spin 0 state. Anyway, then the spin 1 state can be possible. It is also for the spin 1 state is also for the bosonic particle. We call it a spin triplet superconductor. In a spin 0 case is a spin singlet superconductor. Spin singlet, because this state, quantum mechanical state, is a spin singlet state, and also this case is spin triplet state. And it is a spin singlet state, and it is a spin triplet state. It is plus, and it is It is minus. Anyway, and spin singlet is spin singlet state, and the spin triplet state is symmetric. Symmetric, and spin singlet state is antisymmetric, and in spin state. Therefore, in the Cooper pairs are spin singlet formation, because spin singlet is simply described, but the spin triplet state is very difficult, because the spin is very difficult to consider, because it gives a magnetic moment, and we should think about that magnetic properties. But in basically superconducting materials is not a magnetic materials, therefore it is unlikely for the spin triplet state. But like ruthenate superconducting materials and some special superconducting material shows the spin triplet state, but in many cases and many superconducting materials, they do not favor for the magnetic moment. Therefore, spin singlet state is more energetically is more favorable. And therefore, anyway, then the Cooper adopted Cooper pairs for 2 electrons formation for spin up and spin down. And Cooper assumed that it is Fermi surface. It is a Fermi surface with a momentum space. And let's consider only 2 electrons. 2 electrons have the momentum K1 and the other momentum K2. And also 2 electrons are just outside the surface of Fermi C, and also interacting through a weak attractive force, and per weak attractive force. And Cooper assumed that Cooper pair shows that in 2 electrons outside, just outside, because Fermi level is important in condensed matter physics. Just outside the surface of the Fermi surface, and also interacting through weak attractive force. But it is very interesting to adopt it for the weak attractive force, because electron is the minus charge, and 2 minus charge electrons repel with each other. But Cooper bravely assumed that 2 electrons are attractive with each other, and but we do not know at that time. Cooper do not know the why, what causes the attractive force for 2 electrons. Anyway, then he assumed that the weak attractive force, and also to have the bosonic particle. And there are some assumptions. First assumption is that 2 electrons have opposite spin. Two electrons have opposite spin values, and one is a spin up and the other spin down, and total spin is 0. And up down spin, one spin up and the other spin down to have the bosonic particles. It is a requirement to have the bosonic particles. And also second assumption is the neglect all interaction between electrons in the Fermi surface, because it is very difficult to consideration in the Fermi electrons in the Fermi C. But it is natural in many metallic materials, because in metallic materials, and Fermi C is confined at the lattices, and the free electrons is important anyway, and therefore neglect all interactions between between electrons in the Fermi C. And also only two electrons interact with each other. Only two super electrons interact with each other in potential V R2 minus R1, and here one spin up and the other spin down, and also the distance is that R2 minus R1, and the potential is that the interacting potential R2 minus R1 is the interaction for two electrons. It is a basic assumption and also very simple to understand. And also let's consider for the Hamiltonian. And the Hamiltonian of the system is that for one electrons, P1 scale over 2m, and because electrons are same and the mass are identical, and also P2 square over 2m plus potential is that R2 minus R1. Anyway, it is absolute value, and it should have when we make a Hamiltonian, and we should find that eigenvalue problem R1, R2, and T. It is that IH bar partial T psi R1, R2, T. We should find that Schrodinger equation. And also because it is two-body problems, and we can define the reduced coordinate, and let's define that relative coordinate, and R is that R1 minus R2, and here relative coordinate, center of mass coordinate is M R1 plus M R2 over M1 plus M2. Anyway, M1 and M2 are equal with each other, and therefore it is 2 R1 plus R2. Yeah, because M1 and M2 are equal with each other. And also it is relative center of mass coordinate, and reduced mass. Here define the reduced mass is that reduced mass can be simply defined that inverse mass is M1, M2, M1 plus M2, and it is reduced mass is that half M is. And the relative here we can define that the relative momentum in momentum space. It is that Q is that relative momentum M1 plus M2 A1 P1, it is relative momentum minus M2 P2. This is relative momentum And capital P is that the central mass momentum, and the total mass is 2m. By adopting this reduced coordinate and central mass point of view, the transform Hamiltonian have that 2m capital P square over 2m plus 2 mu q square plus potential. It is a simple understanding for two-body materials. And also in this case, let's define that in the psi r1 r2 t has two parts. One is that the f rt, it is f function is the central mass coordinate, and the phi is the relative coordinate. It is a relative coordinate. From this expression, and it is exponential I over h bar, it is a p dot r minus p square over 2m to capital M t exponential minus I epsilon t over h phi r. And it is a result from the quantum mechanics. And the Schrodinger equation, because the central mass coordinate is easily solved very well, and therefore the Schrodinger equation is the only for the relative coordinate, and therefore Schrodinger equation has the form minus h bar square over 2 mu. Here's a relative coordinate square plus VR. It is potential phi r equal to this vector r phi r. It is a Schrodinger equation. Therefore, here because in the central mass coordinate, and the central mass coordinate is that P1 plus P2, it is equal to 0 because there is an attractive force, and in the central attractive force, and two electrons mass are same with each other, and from the law of action and reaction, and this kind of total in central mass coordinate, the total momentum should be 0. Therefore, in other words, it is a P1, it is exactly minus P2. And also here we can say that phi r has an expansion for the exponential ikr because it is a free electron. Because it is a free electron, it is extended wave function, and ak is the for each momentum amplitude is kind of amplitude for respective k momentum. In other words, it's a phi is the summation for k, ak, and k state. And it is very simple to understand, and it is a general quantum mechanical problem. And from the quantum mechanical point of view, we should find that expectation value, and also the Hamiltonian is that from the Hamiltonian problem, h bar square k square over 2 mu plus VR and AK and K state. It is that energy AK and K state, and let's have a broad state for Q state in both sides like this. Then you can find that the expectation value. Then from this from this calculation, the kinetic energy should have the h bar square q square 2 mu and aq because it should have the chronic delta qk, therefore it is q plus potential energy is for the summation for k state and q state and potential and k state and ak equal to energy aq. Therefore, we should find that these matrix elements, we should calculate this matrix element of scattering. It is scattering, matrix elements of scattering. Therefore, let's define that here VKQ is that KVQ. Then here we can define that it is K state and normalization for the square R state and the potential and the prime the prime square and R prime and Q. This can be extended like this, and also this one is a double integration for the dr square and dr prime square and the square and cube, dr cube and dr prime cube, and kr state rv r prime and r prime q. As you know, then the kr is that exponential I k dot r, and the r prime q is that exponential I q dot r prime. Therefore, and also from the quantum mechanics, in the exponential I k dot r is that the solution is given by the spherical Bessel function, and the result, the calculation result is that 4 pi summation for L from to 0 infinity, and m equal minus L to L. This is the result from quantum mechanics, and the I to L y L m star zeta k phi k and the JL KR. This JL means that spherical Bessel function, and the y L m zeta phi, y is that spherical harmonic function, and or in other words, summation L from 0 to infinity, summation m minus L to L, I to the L, 2L plus 1, and JL KR, and P. Here is P means that Legendre function, KR. Here is that spherical Bessel function. Bessel function, and the y L m zeta phi is given by the minus 1 to m 2L plus 1 L minus m factorial 4 pi L plus m factorial, and PLM cosine theta exponential I and phi. It is spherical, and it is a result. Therefore, when we adopted this equation, this potential function, we can summarize the potential function. Okay, Q is that K vector V Q. And I write down the result. It is that integration summation for L M 4 pi I to the L J L K R Y L M K Y L M star R, and also V potential summation for L prime M prime 4 pi I to the L prime J L prime Q R Y L prime M prime star Q Y L prime M prime star R. It is a potential, and so when we rewrite down summation L M integral in dr 4 pi square I square summation L M J L K R V R J L Q R Y L M K Y L M star Q. Here let's denote that this value like the VL KQ. Then it can be write down for summation L M VL KQ and YLM K YLM star Q. And here VL KQ can be defined by the integral dr 4 pi square I square summation LM JL KR VR JL QR. It is defined there. And therefore, and the Schrodinger equation from this Schrodinger equation, and also the wave function of this form, and the Schrodinger equation can be transformed like h bar square k square over 2 mu a k and plus summation because in this case, and the KQ and QK can be exchangeable anyway, where it is for Q summation LM VLKQ is the potential, and YLM K YLM Q AQ is that EAQ. And it is a Schrodinger equation of two electrons, and it is not surprising because two-body problems, the solution is well known like this, and it is when you review the quantum mechanics, and you can easily understand this this formalism. And the important thing is from now on, and Cooper consider potential very simple understanding, and Cooper potential in Cooper pair, they assume that the VL KQ KQ has two potential, and the potential is non-zero for if the momentum KQ is less than certain momentum and greater than the Fermi momentum. And here the momentum k is that the wave vector, k is wave vector, and the q is the relative momentum. Therefore, you can understand that k is that wave number, q is the relative momentum, and in the otherwise the potential is zero. And this is a simple assumption. And also, then when you see the Schrodinger equation and this kind of spherical harmonic function, there is a spherical harmonic function formalism. Therefore, let's define that. A k vector is that a k is a definition YLM k, and lambda L is that potential KQ is the denote that as a lambda. Lambda is a coupling potential, and the Schrodinger equation can be write down as h bar square k square over 2m and ak plus summation q and summation lm lambda l. This is a VL is a lambda l, and so also YLM star q, and AQ, and this one it is that AQ, and it is EAK. Yeah. Therefore, and basically the first term is the kinetic energy, and because there are two electrons, and two electrons, therefore it is that here is mu, not m, it is mu, and mu is that from the reduced energy, reduced mass, mu is that m over 2. Therefore, it is that 2 epsilon k ak plus lambda L. And so we can understand that from the lambda L for respect Q, AQ, then EAK. And also let's find that summation Q over AQ is a C, and let's summation with K. Then this equation can be write down as a K state. Therefore, it is E minus 2 epsilon K AKL equal to lambda LC. Here we define that the summation for KAK is that summation K, therefore summation AK is that E minus 2 epsilon K and lambda LC. And basically you know that it is a C because this one, from the definition. It means that, and the summation for K lambda L over E minus 2 epsilon K should be 1. Here the summation index K is considered only the interval, and also the K momentum is in the K is in certain Kf. It is near the Fermi energy. Therefore, and also there are so many electrons in solid, and this summation can be make integration, and therefore here we define that it is a phi E. Let's define that it is the summation for K 1 over E minus 2 epsilon K, because lambda L is a independent parameter with K. Then the summation can be changeable by the integral in this so many electrons, and can be regarded as a continuous medium from the Fermi energy to the certain energy level, and also density of state should be multiplied and d epsilon, and also E minus 2 epsilon K. Therefore, here the density of state at the Fermi level is very important, near the Fermi energy, and the density of state is a function of the Fermi energy, and also EF to E epsilon A, the epsilon 1 over E minus 2 epsilon K. It is this because the Fermi level is very important. Fermi level density of state is very important, and it is almost constant. From this equation, and also it is that n density of state at the Fermi level, it is minus 1/2 ln E minus 2 epsilon, and from EF to the EA, then it is minus n epsilon f over 2 ln 2 epsilon A minus E, and also 2 epsilon f minus E. And also this definition, this one is a phi, and it is 1 over lambda L, 1 over lambda, because Ln function is always positive, and also therefore density of state also positive value, therefore it is negative value. And what is the lambda L? Lambda L is, from the definition, lambda L is potential. Lambda L is potential between two electrons, and it means that lambda L is negative. Negative means that attractive potential, it is lambda L is negative. It means that negative potential it is surprising result, and electrons interact. It means that electrons attract with each other. And it is very important and also very surprising result. And basically you know that electrons are identical minus charge, and the two minus charge electrons should repel with each other. And Cooper just only assumed that the two electrons have opposite spin, and also there are they are in the near the Fermi energy, and also they have the interaction. Here, then the result is the interact with each other. There is no attractive interaction in here, but when we find that from the quantum mechanical problem, say that they should have negative potential, the attractive force. And how can what in this case, and what causes this negative potential? And it is that it is very difficult to understand. And also, I will deal with what causes this negative potential, and it is come from the phonon energy, phonon, and the phonon attracts two electrons. And therefore, it is very important result, and you should memorize. You should keep in mind that the negative potential is coming from the basic assumption of the BCS theory. And in this case, let's consider for the bound state energy, and also in here we calculated and the bound state energy. Can be defined at 2 Fermi energy minus 2 delta. It means that Fermi energy, this is a Fermi energy and delta. There is an energy band gap, and because, as I said, and the superconducting state is energetically favorable comparing to the normal state in the superconducting state. Therefore, the energy gives free energy. We already know that this is normal gives free energy, and in the superconducting state, and the superconducting state gives free energy is lower, and therefore the energy lowers, and the energy difference means that the energy band gap. Therefore, the energy band gap is coming from the superconducting condensation of two electrons, and therefore this delta is the condensation energy. And also from this result, let's consider for minus n EF of 2 and n, because energy can be defined like this, and also EF minus E is that 2 delta, and also in the numerator 2 epsilon A minus 2 epsilon F plus 2 delta, and it is a negative potential, 1 over VL. Here we assume that VL is positive. Then we can say that here epsilon A minus epsilon F over delta plus 1 equal to exponential 2 over n EF of VR. Therefore, finally, the delta is that EA minus EF over exponential 2 over n epsilon F VL minus 1. It is energy gap. Superconducting energy gap. Superconducting energy gap. And from this equation, and for strong interaction, and the large energy gap, and also large density state at the Fermi level gives that also large energy gap. Therefore, in the superconducting, in order to have the superconducting state, stable superconducting state, it needs a large density state and a large potential between two electrons. And here, and typically, and VL, if VL is proportional to the kBTC, TC is a superconducting state, and if you assume that TC is about 10 Kelvin, and in energy it is a 2 milli-electron volt, and the energy gap is about EA minus EF, and exponential in the approximation it is minus 2 over n epsilon f VL. Then it is over omega d and exponential minus 2 over n epsilon f VL. Then it is order of 0.1 Kelvin, and for the Debye frequency is about the Debye energy is about 300 Kelvin. And even though VL is very small, and the attractive interaction is generated, and the Cooper pair is energetically favorable. Therefore, it is very important. Anyway, this result is very important in the superconducting state, and the Cooper pair. Cooper demonstrated that when we think about the two electrons in the outside of Fermi surface, and there is an interactions, and they should have the bound state. Even electrons should have the attractive interaction, and some kind of photon energy make an attractive potential between two electrons. That is Cooper pair.